All right, welcome back. Today's day 2 of our stoichiometry review. And today we're going to be talking about percent yield. Well, yesterday the central question that we were asking was, given two reactants, which one will run out first and how much product can we make? And the example that we used was hydrogen and oxygen producing water. And we said if we had a certain amount of hydrogen and a certain amount of oxygen, which one would run out first and how much water would we actually get? And that amount of water that we would actually get, we called the theoretical yield. The yield that we would theoretically obtain by doing this particular chemical reaction. Today the question is, what actually happens when someone runs this reaction in a real lab? And we can think about it this way. If we have two containers that represent the theoretical yield, what we ought to be getting through our calculations, and our actual yield, what we got by doing the reaction, how do we identify effectively this gap here, the distance between what we got and what we should have gotten? And how do we interpret our real lab data honestly? Now this gap here is called the percent yield. And that's going to let us know the difference or the comparison between what we should have gotten and what we actually obtained. The handout that you're going to be getting has 4 parts. Parts 1 through 3 go with this video, and part 4 is an independent practice after the video ends. It also comes with homework, of course, homework. So here's what I need you to do. I need you to make sure that you have this student handout in front of you. I need you to make sure you have your periodic table. You need to make sure you have your calculator. Go ahead and do that now. All right, assuming that you have all of the required materials, let's go ahead and start at part 1 with the warm-up. Okay, so if you haven't yet attempted these on your own before watching this video, go ahead and pause the video and do that now. All right. So for part 1, questions 1 and 2, before I give you the answer, I want to make sure you see where the percent yield formula actually comes from. Question 1a is asking you, what fraction of the theoretical yield did the student collect? With a theoretical yield of 45.0 grams and an actual yield of 38.2 grams. In the case of percent yield, we are going to be doing not quite the part over the whole times 100 per se, though we are going to be doing something similar to that. So think about this. When you take a test, right, there's a certain amount of points that you can earn. Let's say your test is out of 25 points. And let's say you only earned 23 of them, right? You could calculate the percentage by doing the division, what you got over what you should have gotten times 100, and that gives you your percent. Percent yield is going to be very, very similar. Percent yield is going to be your actual yield or your experimental yield over the theoretical yield times 100. Okay. So in this case, question 1a, it asks what fraction of the theoretical yield did the student actually collect? And the way that we're thinking about that is, well, we only got 38.2 grams out of our total ideal 45.0 grams. And so when you do this, you should end up getting 0.849. And now we want to convert this to a percentage, and we just do that by multiplying by 100. And we get 84.9%. Great. And so this is the formula that percent yield uses, right? It's the actual over the theoretical times 100. And that formula lives at the end of every limiting reagent problem from here on. So you're going to find the theoretical yield the way that we did last class from the limiting reagent, and then you will compare that to what was actually collected. So for question 3, which brings us back to day 1, we want to use the aluminum chloride reaction that we did last time. The theoretical yield was 18.8 grams, and the student collects 15.1 grams. Calculate the percent yield. Well, the way that we do that is by saying, what did we actually get over what we should have gotten, what we calculated, right? And so that's going to be 15.1 grams over 18.8 grams times 100. And that gives us our answer. And you should have gotten 80.3%. Now here's another question. Is this a good result? We're going to come back to that later, but for now, I want you to make sure you have this answer in your box, and you want to keep that question in mind. Is this a good result? All right. Let's continue on to the next page, part 2. So, based on what we just talked about, we want to think about what is a theoretical yield. A theoretical yield is the maximum amount of product predicted by stoichiometry. It's the maximum amount of product predicted by stoichiometry. And this is, of course, assuming that the reaction goes to completion and nothing is lost. And we'll talk more about that later. The actual yield, on the other hand, is the amount of product actually collected from a real experiment. The amount of product actually collected from a real experiment. Okay? Remember that percent yield is the actual yield divided by the theoretical times 100. Okay? That's the key point here. The actual over the theoretical times 100. Theoretical yield is what the math promises, whereas actual yield is what ends up in the flask. It ends up in your final result in the real, actual experiment. And percent yield then measures how close these two things are together. Right? So there's a bunch of different reasons why you might not get a 100% yield. And this will happen all the time. It's very rare that you get 100% yield. Okay? And so I want to give you those 4 major reasons now. I might ask for those on an assessment, so you want to make sure you know them. The first reason is you might have an incomplete reaction. Right? An incomplete reaction means that not all of the reactants convert to products. The second thing that might happen is that you have a side reaction. This means that reactants will form unwanted byproducts instead. This could mean that you're reacting with the atmosphere, like in the case of our copper sulfate pentahydrate lab. If you heated it up too much, it would end up reacting with atmospheric oxygen and turn that brownish black. Right? I believe one group in particular did that and had to restart. Right? That would be an unwanted byproduct. Okay. Another reason why you might not get 100% is from transfer losses. Right? If you remember when we did our separating mixtures experiment in the last semester, one of the things that happened was that not everybody got all of their sand. The separating mixtures was when we did the magnetic iron mixed with the sand, mixed with the salt, and you had to separate them out via filtration and magnets and then boiling all the water off from the salt so that you would get those three things individually. Right? You remember that? Some people didn't get all of their salt transferred, or some of their salts sprayed out of their beaker, or they didn't get all the sand transferred, right? So in this cases, product can be left on glassware or on filter paper or on different kinds of equipment. And so when you transfer your substance from one vessel to another, you may lose some in the transfer. And lastly, we could potentially get a measurement or collection error. And in these cases, with the measurement or the collection errors, what ends up happening is that product is lost during filtering or drying or weighing. And so we end up losing some in the process, right? These are not really excuses necessarily. They're real physical and chemical phenomena, right? And so in many cases, certain kinds of reactions only go to a certain amount before they stop for various reasons, right? It may be the case that certain things only react 78% of the way before they stop. And that means that if you actually get a 78% yield, you've done a really great job, right? So this is just the way some things happen. It's pretty interesting. So let's keep continuing on. Can percent yield ever exceed 100%? What do you think? In theory, can percent yield ever exceed 100%? I mean, no, that wouldn't really be possible, right? Why is it not possible? If you said the law of conservation of mass, you'd be right. Consider this scenario. In this case, I might have a certain amount of starting reactants. So take this example where I have 0.63 grams of hydrogen and I have 5.00 grams of oxygen. Now in this scenario, what ends up happening is these will react completely with one another. So neither of these are the limiting reagent. This is the perfect amount of each of these substances, right? What if I got 6.00 grams of water? Would that make any sense? No, it wouldn't make any sense. I would be getting 5.63 grams of water, right? Because what we add up on the left must equal what we get on the right. This is the law of conservation of mass. Matter can't be created or destroyed. Right, so you cannot collect more substance than stoichiometry allows, right? But in some cases, we may get more than 100% over here in our reactions. And if that happens, that means that the sample is impure or perhaps it's wet, right? So we might get more over here than we were expecting, right? And so that does happen sometimes. Okay, that should have helped you fill out your blanks for section B, right? The first one, in theory, percent yield cannot exceed 100% because the law of conservation of mass. or you cannot collect more than stoichiometry allows, right? However, a student might report greater than 100% if the sample is impure or wet. All right, so let's keep on going. We're down at section C now. So follow along and fill in the calculation chain on your handout. This problem here is going to combine everything from last class with today's new step. So in this case, we have a reaction where magnesium and oxygen yield magnesium oxide. And it's already been balanced for you. You're welcome. And so let's say we're given 10 grams of magnesium and 8 grams of oxygen. And our actual yield collected is 11.4 grams of magnesium oxide. Well, what do we have to do here? Well, let me write some of these things down because I always like to start from my balanced chemical equation. So if we have 2 magnesium and 1 oxygen yielding 2 magnesium oxide, and in this case we have 10.0 grams of magnesium and 8.00 grams of oxygen, right? We have to first determine what is the theoretical yield, and we do that by finding the limiting reagent and calculating the theoretical yield from the reagent that is going to run out first, and then we can compare that to the actual yield collected. So let me start off with magnesium first. 10.0 grams of magnesium. And you'll remember we just go through this the same way we always do. We're going to convert this to moles. Right? 1 mole of magnesium is, I got to remember this, it's 24.31 grams. 24.31 grams of magnesium. And then for every 2 moles of magnesium, we get 2 moles of magnesium oxide. So 2 moles of magnesium gives us 2 moles of magnesium oxide. And then we can say 1 mole of magnesium oxide is a certain mass, right? We do that by adding up the mass of magnesium and the mass of oxygen, which should be 40.31 grams of magnesium oxide. And so when I'm putting this in my calculator, I'm doing 10 times 2 times 40.31 divided by 24.31 divided by 2. Right? Or if you prefer, 10 divided by 24.31 times 2 divided by 2 times 40.31. Right? The choice is yours. Because PEMDAS, right, groups multiplication and division and addition and subtraction together, it doesn't matter what order you do these in. It doesn't matter what order you do these in. Right? You can do them in any old order. 10 times 40 divided by 2 divided by 24.31 times 2. Doesn't matter. Right? You can do whatever you want. All right. When I do this all in my calculator, I should get 16.6 grams of magnesium oxide. Let's do the same thing now with oxygen. We've got 8.00 grams of oxygen, and the molar mass of oxygen is 16, but wait, we've got 2 of them here. So that's going to be 32.00 grams of oxygen in 1 mole of diatomic oxygen. And then for every 1 mole of diatomic oxygen, we get 2 moles of magnesium oxide. So 1 mole of oxygen gives us 2 moles of magnesium oxide. And then for every 1 mole of magnesium oxide, we have 40.31 grams of magnesium oxide. And when we do this in our calculator, we should get 20.2 grams of magnesium oxide. So the magnesium is my limiting reagent, and that means that 16.6 grams is my theoretical yield. Now, the problem says that what I actually collected, my actual yield, is 11.4 grams, whereas my theoretical yield is calculated at 16.6 grams. And we know that percent yield is equal to the actual over the theoretical times 100. And so we can do 11.4 grams divided by 16.6 grams times 100 to get my percent yield. Right? So a lot of this should seem familiar to you. A lot of it should just be what we did last time. Nothing crazy. This is the only new step. And this new step puts us at 68.7%. Great. Let's keep on trucking. Section D. So, percent yield of 85% is, do you think this definitely means the student made an error? Do you think it may reflect normal lab losses? Do you think it's impossible? Go ahead and circle one. So, the answer here is that it may reflect normal lab losses. 85% is perfectly reasonable for many reactions, and it's not a sign of error or that you did something wrong necessarily in most reactions. Before you judge whether or not a percent yield is good or bad, you have to take a couple of different things into consideration, right? You might want to consider what kind of reaction is it? Is it an inherently incomplete reaction? Right? If you go on to do chemistry in college and you take organic chemistry, in some cases you'll be lucky to get 32 or 35% yield. In other cases, in your analytical chemistry classes, if you don't get within a 0.1% yield, you're going to have to do it all over again. Right? So it just depends on the kind of reaction that you're doing. What kind of reaction is it? The second thing to consider is, what are the lab conditions, right? Do you have really pure reagents? Do you have really precise measuring tools? A graduated cylinder, though it is for measuring volume, is not a super precise measuring tool. And so in that particular instance, you might say, well, of course we're going to not get a perfect 100% yield. We didn't have a perfect measuring tool. This is very typical. You can also ask the question, was the product fully dried? Was it collected well? You might also say, what do other chemists typically achieve for this reaction? Right? So percent yield is not a grade. It's a data point that requires a bunch of context to interpret. Right? So in 1 to 2 sentences, I want you to explain what information you would want before judging whether a percent yield is acceptable. You can go ahead and pause the video and write this down now. 1 or 2 minutes. All right, so if you've taken a couple of minutes to write down your answer to what information you would want before judging whether a percent yield is acceptable, we'll go ahead and move on to part 3. Why don't you go ahead and work alongside me in this video. Follow along here. So the question here is that iron reacts with diatomic sulfur to produce iron 2 sulfide. If we're given a certain amount of iron, a certain amount of sulfur, and the actual yield, we want to do three things here. We want to write and balance the equation. We want to identify the limiting reagent and the theoretical yield. And we want to calculate the percent yield. You've already seen me do this, but I still want you to follow along with me. All right, so I really encourage you, no, I demand that you start with the balanced chemical equation. So here we have iron reacts with diatomic sulfur to produce iron 2 sulfide, which I already told you what the formula is for that. You're very welcome. All right. How do we go about solving this? Well, we'll put a 2 here, and we'll put a 2 here. There we go. So now what we'll do is we will go ahead and identify the limiting reagent. Okay? We're told that we start off with 22.4 grams of iron and 18.0 grams of sulfur. All right. So I want you to go ahead and try this on your own, starting with the iron, to see if you can figure out what the theoretical yield is here. Go ahead and try it, and then I'll come back in just a minute and go through the whole problem with you. All right, it seems I made a bit of an error here, which I have corrected in your worksheet, but I have not corrected in mine. So the sulfur is not actually diatomic. It's not a real thing. So if it is Fe plus S yields FeS. Sorry about that. Let's, if you need time to redo that, please go ahead and pause the video and do that now. My apologies. All right, so if you've done that, then we can go ahead and calculate from each reactant. So we've got 22.4 grams of iron and 1 mole of iron is 55.85 grams of iron. For every 1 mole of iron, we get 1 mole of iron 2 sulfide. Remember, the 2 just tells you the charge. And then from there, we can say 1 mole of iron 2 sulfide weighs 87.92 grams. Okay, we plug that into our calculator and we should get 35.3 grams. We can then do that with the sulfur. We start out with 18 grams of sulfur, and when you do that calculation, you should get 49.3 grams. So iron is our limiting reagent. This is our theoretical yield. And then we can go ahead and we can calculate the percent yield. And we do that by taking what we actually got in our experiment, which I'm looking at the question, 28.6 grams, what we actually got, over what we should have gotten, which is 35.3 grams, times 100, and we end up with let's see, 81.0%. Great. Now you've seen a bunch of problems like that. That should be pretty straightforward. Now we've got one that's a little bit more complicated. All right, so let's look at part 3, question B on the next page here. This says that a student synthesizes aspirin, which is C9H8O4, with a molar mass of 180.16 grams per mole. And they report a percent yield of 72.0%. Their actual yield collected was 14.4 grams. And what we're looking for is what is the theoretical yield? And so the way that we can do that is we can say that percent yield is equal to the actual over the theoretical times 100. We know the percent yield, we know the actual yield, but we don't know the theoretical. That's what we're asked for first. So all we have to do is rearrange these terms. I'll multiply both sides by the theoretical, and I'll get T times the percent yield equals A, the actual yield, times 100. And then I can divide both by the percent yield, rearranging this to get the theoretical yield is equal to the actual over the percent yield times 100. Awesome. So, just fill everything in. We have 14.4 over 72 times 100. And that should give us our percent yield. So this is 72 over 100, because it's a percent. My apologies. Great. And so the result here should be that our theoretical is 20.0 grams. So, parts B and C ask you to convert these yields to moles. Okay, so because they're in grams, we should be able to easily convert these. Right? So let's look at part 3, question B, part B. How many moles of aspirin were theoretically expected? We got 20.0 grams of aspirin, and we know that the molar mass is 180.16 grams C9H8O4 in 1 mole of C9H8O4. And so when we do that, we should get 0.111 moles of C9H8O4. Nice. When we do this for the actual yield, we do the same thing. The actual yield was 14.4 grams of aspirin and so we'll just divide by the molar mass and that should get us 0.0799 moles. Great. The cool thing about this is that we can actually divide these to get the same percent yield. So if I take 0.799 divided by 0.111 times 100, I'll also get 72%. Great. This is the end of the video here. Before you move on to part 4, you should go ahead and complete. Actually, no, just go ahead and complete part 4. Yeah. Once you're done part 4, you can go ahead and get started on the homework, which is at the end of this packet. Think about what we said in section D. Percent yield does not exist in a vacuum. Think about what kind of reaction each student might be running, what honest lab work looks like, and what a suspiciously high yield might sometimes mean. Um, the part 4 that you're going to do has some independent practice problems. They'll escalate in difficulty, right? So the last two are going to ask some pretty conceptual questions. One of them is going to be about why two products from the same reaction can have different percent yields, and one is going to be a combustion reaction with two separate products. Those are the kinds of questions that you can expect on assessments, so don't skip them. Remember that if you're getting stuck, you can check 3 things in order. First, your balanced equation. Second, your limiting reagent identification. And third, your molar masses. Almost every single error is going to trace back to one of those. Good work today, and I'll see you soon.